You have fallen into Event Horizon with John Michael Godier. John is joined today by Niayesh Afshordi and Phil Halper. Niayesh Afshordi is an assistant professor in the Astrophysics and Gravitation group at the Department of Physics and Astronomy at the University of Waterloo, and an associate faculty member in the Cosmology group at the Perimeter Institute for Theoretical Physics. His research spans dark energy, dark baryons, and the cosmic microwave background, with a focus on identifying anomalies that could point towards new physics. Phil Halper is a Fellow of the Royal Astronomical Society and Science Popularizer. He is the creator of the popular YouTube series Before the Big Bang. His astronomy images have been featured in major media outlets including The Washington Post, the BBC, and The Guardian. He has published several papers in peer-reviewed journals.
Niayesh Afshordi and Phil Halper, welcome to the program.
It's a pleasure to be here. Thanks, John.
Thanks very much. It's great to be on.
Now, gentlemen, you have an interesting new book out, Battle of the Big Bang, New Tales of Our Cosmic Origins, exploring the history of Big Bang cosmology and the history of the science itself and the science, of course. But I have one overarching, very difficult question that I often ask physicists and get different answers, and that is, what happens before the Big Bang? Is there a possibility of something before it? Or is it a timeless singularity where the question becomes meaningless is usually the answer that I get. What are your views on it? Starting with you, Dr. Afshordi.
Well, that's an excellent question. That gets into the heart of our book. And I guess if it was a short answer, we would have a very short book. Fortunately or unfortunately, it's not a very short answer. But actually, I'm going to start with something that's not in the book, which is the survey we did last year, last August with Phil in Copenhagen. So there was a big conference focusing on various topics related to fundamental physics and black holes. And we asked audience a few questions, 12 questions to be precise. And one of them was, what do you think happened at the Big Bang? Or what do you think the Big Bang is, in fact? And that was the only question that there was a consensus answer, in the sense that there's a majority answer. And majority thought that Big Bang is the theory of universe starting from a state of hot and dense, basically medium. And basically less than 20% of people thought that Big Bang either was the beginning of time with a singularity or without a singularity. And singularity would be a point where you have infinite density. So 68% of physicists from a wide range of disciplines believe that Big Bang doesn't really say what's happening at the beginning of time or whether there is a beginning of time. So the answer to your question, the short answer is we don't know. It is the frontier of our knowledge. We're doing our best. We're trying to push the frontiers as much as we can. But asking that question is meaningless is very presumptuous because we don't have the answer to that question. And that is why this is such a fascinating area of inquiry that's bringing in so many people from so many disciplines. To be honest, as far as religion and arts to various areas of science, from astronomy to fundamental physics. So I don't know if that's the answer you wanted, but that's the answer I got.
Anything to add to that, Phil?
Yeah, I think this is a case where we have one of the biggest gaps between what the public understanding of science is and what scientists themselves actually think. So I think the public understands the Big Bang to either mean the theory that says there was a beginning of time, or even that the universe came from nothing. Recently, Joe Rogan was saying, the Big Bang requires a miracle because it says the universe came from nothing. We also had Sean Carroll on Piers Morgan's podcast, and Piers Morgan was like, explain how the universe came from nothing, what was before nothing. And, the Big Bang Theory doesn't say the universe came from nothing. It just says it came from a hot, dense state. Now, there are these singularity theorems that were proven by Penrose and Hawking in the 60s and 70s that say, yes, there was a beginning of time. that there was a singularity. But almost everybody thinks that these theorems are inapplicable, including Penrose and Hawking themselves. And I know because I sat in their offices and talked to them. So no one believes that the singularity is actually real. We can go into why, what are the assumptions of these theorems that supposedly say the Big Bang was the beginning of time. And therefore, if you ask the question, what came before, just shut up, it's a meaningless question. But we think it is a legitimate question, because if these singularity theorems can't be trusted, and most physicists think they can't be trusted, then it's completely open that maybe there was a before the Big Bang. And in our book, we explore many of the different possibilities that physicists are now exploring.
Now, removing the singularity from the equation, you get ideas like the Big Bounce, where it never actually becomes a singularity, it simply rebounds. After eventually, say, gravity eventually is able to overcome dark energy. And we know now that dark energy's values seem to be changing over time. So if it recollapses, then you get a big bounce. Explain that theory a little bit better than I did.
So maybe I can go first in this. I think you were falling to the same track that others get. We don't know a lot of things. Now, I think we know to good approximation that there is a dark energy. Whether we know that dark energy is changing or not, I think the jury is still out on that. I mean, we see the press releases and such, but this is such a new discovery, and these things come and go, and sometimes they stick. But even if they stick, that's just says the dark energy may be changing now, but will it keep changing into the future at the same rates? We don't know. But that doesn't prevent us from speculating about the cycles of time. Now, that there were two different things that you mentioned in your question. You mentioned the bounce, and then you mentioned what happens in the future. Can the universe repeat itself? And those are two different things. So you could have a bounce that suggests that basically instead of a bang, bang, I guess, depends on what you mean. But instead of a singularity where the universe starts from this infinite density state, you kind of have a collapsing or contracting universe that kind of reaches some maximum density and then a stop and it starts expanding. And that's what appears to be the Big Bang for us. So that's certainly possible in some theories of quantum gravity. This has been argued that this would happen like in loop quantum gravity. My colleagues in this building, like Carl Roveri, who's at this conference that I am right now, he was one of the developers. Abu Ashtekar was who kind of been promoting this loop quantum cosmology or loop bounce. He's gave a remote talk here. Other possibilities is that if you could make gravity repulsive in some phases, like my wife Ghazal Gassinjani, she's proposed this Kaskutan bounce, which is a way that gravity can become repulsive in some states. So that's a possibility. And there are various ways of doing that to avoid the singularity. Now, whether it's generic, we don't know, but there are certainly models that could do that. Now, the other thing about whether the universe can repeat itself going to cycles, so there is an idea that maybe at some point into the far future, dark energy would turn negative. Now it's positive, it's speeding up the cosmic expansion. If it somehow and it goes to zero and go negative, then it could stop the cosmic expansion and the universe can recollapse. That's a possibility. We don't have any direct evidence that may happen into the future. This is always the thing about the future. It's very hard to predict it. The hardest thing to predict is the future, it turns out. But so that's one way that the universe can go into cycles. But there are even more creative ways that the universe can go into cycles. Maybe it doesn't have to recollapse. It could become infinitely big. And then you somehow start a Big Bang from this infinitely big universe, which seems very bizarre. But one of the originators of singularity theorems, Roger Penrose, who Phil mentioned, in fact, proposed that you can go from an infinitely big universe to an infinitely small universe. And that could lead to cycles. So those are possibilities, and then our job is to try to make those possibilities precise and see whether there are observational evidence for them.
Well, I think the bounce idea has to be separated from the cyclic universe idea. So think of it this way. If we have a bounce, you could have a universe that looks like an hourglass. So we have an expanding universe on one side of the hourglass, expands out to infinity, and the other side of the hourglass is contracting from infinity. So it doesn't have to continue sort of bounce, rebound, bounce, rebound. We could just have this the whole universe could look like an hourglass. So that's one thing to keep in mind. Now, the discovery of dark energy changing over time is very, very new. In fact, I was super lucky that the DESI group who had this discovery, they contacted me and said, we've got some new results and we want to announce them on your YouTube channel. So I was super lucky. I got to interview them and I knew the results like 2 weeks before, but it was under embargo. So I had to like have the video recorded, ready, and re-released on the day of the embargo. But what we have to remember is that any new result, we have to wait for other teams to confirm it. So there are lots of new experiments coming online, like the Euclid satellite, the Rubin telescope, various projects, and we'll see if they confirm it. Now, the new results that we're very excited about from DESI, the Dark Energy Spectrographic Instrument, they're at a high level of significance, not quite high enough to be like a full discovery, but it's getting there. It's getting closer. So that's why people are very excited. But even if they got to that sort of what's called the 5 sigma level, we still have to be a little bit skeptical because maybe there's some flaw in the way they're doing the data. And so we want to check other teams, see if they confirm this finding or see if it goes away. Because actually most exciting new discoveries in physics turn out to go away in the end. You know, very few actually stick. But there are reasons to think this might stick. It's not completely crazy and the evidence is mounting. But if it goes away, you could still have a bounce. One of the things that I find intriguing about the bounce possibility is that what we really want to sort of analyze the Big Bang is a quantum theory of gravity. So this is something that combines Einstein's theory of general relativity, that's our theory of gravity, if you like, that's the physics of the very big. Combine that with the physics of the very small, quantum mechanics. And it turns out these two theories, the pillars of modern physics, if you like, don't agree with each other. They actually contradict each other. So physicists want to put them together and have this quantum theory of gravity. There is no... People often say we don't have a theory of quantum gravity. And in some sense, that's true, in the sense that we don't have a well-verified, complete theory of quantum gravity. But we certainly do have proposals that people are working on. Things like string theory, loop quantum gravity. Those are the two most famous ones, maybe because they were... in the Big Bang Theory sitcom, and you may remember that Leslie left Leonard because she was a loop quantum gravity fan and he was a string theory fan, and she stormed out the room saying, "How will we raise the children?" So those are the two most famous ones, but there are others that we cover in the book, Herjava-Lifshitz gravity, causal set theory. So there are other proposals, and what does keep popping up is this idea of a bounce. It's not universal, certainly not every theory implies it, but it does come up in more than one theory, if you like, or more than one way to analyze the Big Bang. So to me, that puts it in the plausible category. We certainly don't know if it happened, but people are working on this and trying to find out, are there predictions? Can we actually test this? And so I'm super excited about it, but of course, always with some caution.
Now, within cosmology and within everything in science, actually, this pervades all of science, and that is repeatability. But the one thing that may not be repeatable, it seems, is the Big Bang. What are your views on that? In other words, do you think this is one Big Bang, or do you think that there were many, either cyclic or a multiverse, however you wish to take it? And do you think that there are other universes and that this is repeatable?
That's an excellent and fascinating question. Indeed, what you suggested goes to the heart of what we do as a cosmologist, that is really cosmology a science, or is it the science in the sense that the other sciences are? Because we do have one universe. And like usually when we do establish other scientific things, we want to have an experiment, we have controlled experiment, we control things in a apparatus, make sure the temperature is right, the pressure is right, and do some experiment, observe the result, and then repeat it. And then various groups want to repeat the same thing. And then we see it becomes established that, okay, this is what's happening. Of course, I mean, even when it comes to astronomy, we cannot do that because we cannot really control the conditions of the sky. Astronomy is older than cosmology in some sense. And we kind of come up with things that we can repeat in some sense. Like we have, I mean, every star is different from every other star, but we observe hundreds of thousands of stars, and then we kind of establish patterns with them. So in that sense, people are confident and comfortable with saying that we understand, say, why the sun shines. Okay, so that's even though we cannot directly go and see there an experiment. Now, when it comes to the Big Bang, in some sense, it's very similar that we are going on a limb, that we're not in the traditional confine of scientific method as we were doing it before. But in spite of that, we think we have kind of established some set of rules that seem objective and repeatable. And that doesn't involve us kind of scrutinizing the universe with, scalpels and pins and needles, but rather what we do is we have these theoretical frameworks which make different predictions, and then we go out and test these predictions. So the idea is that you want to have one unified framework, or if you want, a skeleton for the universe. And then this skeleton, it comes from some mathematics, but it tells you, it predicts different things. For example, the standard cosmological model that we use, which includes a constant dark energy, it includes a dark matter, and includes basically some assumptions for initial conditions of universe. There are 5 parameters in it, basically, that we have to assume. But it predicts lots of things. It predicts the fluctuations in the cosmic microwave background, this afterglow of the Big Bang. It predicts how big they should be, how they should look like. Basically, there are these acoustic waves that propagate in the early universe. But then it also predicts the gravitational deflection of light across the cosmos, the so-called gravitational lensing. It also predicts the number of galaxies and then how they're distributed across the universe. So there are basically a dozen or 2 dozen different things you could look at to test this kind of unified 5-parameter framework. And in each of those kind of data sets, there are hundreds, if not or thousands of independent data points. In fact, you may argue millions. We have observed millions of galaxies now. And they all are independently testing the same underlying unified framework. So in that sense, we have generalized our kind of definition of science in a way that I think most physicists are comfortable with. There are still, some physicists may not be too comfortable with it. Famously, Landau, a famous Russian physicist who won a Nobel Prize, said that cosmologists are never in doubt, but are always wrong, but never in doubt, if I remember, are often wrong or never in doubt. But still, we are pushing things. And then when it comes to the Big Bang, we are still kind of clawing on straws, because we are starting to run out of data. And then we need more data, but also better theoretical framework. And as Phil was saying, one of the sticky points is this quantum theory of gravity, which prevents us from having a good theoretical framework to unify basically data and theory.
Phil, you think there's a multiverse?
Yeah, so let's focus now on the multiverse. I think whether you think we live in a multiverse is going to depend to some extent on whether you think the leading sort of theory of early universe cosmology called inflation is right or not. Because multiverse seems to arise from inflation. But the big question is, did inflation happen? There's maybe a minor question, does inflation actually lead to a multiverse? I think there's a pretty broad consensus that it does. I can only think of 1 or 2 cosmologists that think it doesn't, but they do exist, so we have to keep them in mind. But I think the majority view is that it does. So first of all, maybe we should explain what is inflation, and then briefly say the pros and cons of it, and then how does it lead to a multiverse. So, all right. Inflation is the idea that there was this incredibly rapid period of expansion. And now most textbooks will say it happened just after the Big Bang. But actually, we argue that it happened before the Big Bang. And the reason for this is that, think back to that survey Niayesh mentioned that we did in Copenhagen. We asked cosmologists, what do you think the term Big Bang means? And they said, it just means the universe evolved from a hot, dense state. Now, in inflationary cosmology, the universe only gets hot when inflation ends. So if that's what the Big Bang is, when the universe, was evolved from this hot, dense state, then inflation happens before that hot, dense state. So inflation is, if you like, a pre-Big Bang model, even though a lot of textbooks don't seem to think that. But I think that's because when Alan Guth discovered inflation, this wasn't first appreciated. So he gave talks saying something like 10 to the minus whatever seconds after the Big Bang. But even now, when I've interviewed Alan Guth, he's actually thinking, no, he calls it a prequel to the Big Bang. That's his own term. Although, of course, if we think Star Wars, you might be thinking prequels aren't so good. But hey, some people like them. Anyway, so inflation was very, very popular and still is, because it's supposed to solve various puzzles in cosmology. So perhaps the most important one is, how does this network of galaxies that we see across the cosmos form? Why wasn't the Big Bang really smooth and uniform? So inflation says, well, there were like tiny, this is really mind-blowing, really mind-blowing. There were these tiny quantum fluctuations, but because inflation is so rapid and stretches the universe at such an incredible rate, it stretches these quantum fluctuations so that some regions of the cosmos are slightly overdense, slightly underdense, and that forms the seeds of galaxies. And this is certainly the most popular theory of how the seeds of galaxies were formed. Now, a lot of cosmologists will say that we've actually tested the theory of inflation. It makes lots of predictions, and they've all come back exactly as the theory says. So, and in fact, I'm not just, when I say a lot of cosmologists, I don't just mean the people in the inflation camp. I mean, NASA on their website said, we have detected a signature of inflation. The European Space Agency, I interviewed George Eustathio, who was the spokesperson for their Planck probe, which is the most recent probe to look at the cosmic microwave background. Very, very, it backs inflation. But there's a camp of very serious senior cosmologists who say, not so fast. That actually the theory of inflation has lots of problems. Maybe there's too many different inflationary models. So of course, some of them are confirmed by the data, but if they weren't, the other ones would be. And we come to this multiverse issue, because actually when I've interviewed the critics of inflation, it's the multiverse that's their big bugbear. So let's just put a pin on that for a second. How does inflation lead to a multiverse? Think of it this way. Imagine you have a cake. In fact, we put this analogy in the book. My mum makes this fantastic chocolate cake. It's really yummy. So she puts the cake down on the table and everyone gets a slice. And then we've had our slice, there's half the cake left. And then we have a second slice and now there's no cake, because you can't have your cake and eat it, right? But imagine what would happen if the cake more than doubled in size in that intermediate step. Then we could have our second piece, and then it did the same. It doubled in size again. We could have a third, fourth, fifth. I mean, it would go on forever. As long as the rate of new cake is quicker than our consumption rate, we can have our cake and eat it. And this is what's thought to happen in inflation. So remember we said that it heats up the universe, and our Big Bang is that moment that inflation ends. But the point is, it only ends in one region at one time, but other regions it's still going on. And those regions where it's still going on, it's undergoing exponential expansion. So as long as the exponential expansion is faster than the rate of the decay, then you will create an infinite number of universes. And according to most inflationary cosmologists, any successful theory of inflation is going to have that property. Now, there is some dispute about that. There are one or two. Slava Mukhanov is someone that disputes that. But I think the majority of inflation cosmologists say, yes, this is a generic property of inflation. So it's all going to come down to whether you like all these pluses of inflation, like it can solve these problems, or whether you think these problems, like, there's too many inflationary models, or the very fact that we lead to a multiverse means that we can't predict anything anymore, because, hey, anything that can happen will happen, and will happen infinitely many times. So how do we make sense of the statement that inflation predicts anything? So my own personal view is that, wow, there are really good arguments for and against, and that's what makes it so exciting.
It really does. It really does. It makes it very exciting. Now, Niayesh, you said something very interesting, that a lot of physical theories in cosmology turn out wrong, but there is one elephant in the room that seems to continue to turn out right. And it blows my mind to this day when you really understand it, the theory, and that is general relativity. And that we see that it predicts, or it describes, it gives us a description of gravity in a certain sense, but it doesn't appear to be complete. And that gets back to the quantum theory of gravity that we require here. Do you think, now some people have made the argument that you don't need one, that you don't need a quantum theory of gravity. But to me, it seems almost like you can ignore it because it's so weak on the quantum scale. Maybe that's what they're thinking. But what's your view on that more in depth?
Well, it's actually interesting point of view of how you want to deal with life, I suppose. I mean, humans live their lives for thousands, if not millions of years, and kind of not knowing about what's going on around them and trying to ignore this. And of course, as you learn more about what's going on around you, you learn more that's kind of what are the things that are happening. Some of it may be kind of abstract, but at some point, the more you learn about things, the more you know, what could affect your life. For example, we couldn't forecast weather before, or storms or hurricanes and things like that. But nowadays we have a weather forecast, and we could kind of predict if there are storms coming, and that requires us paying attention to what's going on around us. Now, most of the time you could ignore it. Most of the time you're not in the path of a hurricane or in the path of a storm, but sometimes you are. And our knowledge of what's going on around us actually does help us kind of anticipate good or bad things that might be coming our way. Quantum gravity is kind of like that yeah, we have general relativity indeed has been very successful. We can use it to explain a lot of things, especially on larger scales, from how GPS or solar system works or satellites that go around Earth, all the way to the largest distances in the cosmos. And okay, so there we had to add like one or two knobs, like this dark energy thing as a surprise or dark matter. But they still fit within the framework of general relativity. You just have to add these extra things, but still everything fits, as I said, hundreds or if not thousands of data points. But then the question is, okay, so the fact that things have worked so far, does it mean that you just can ignore the things that don't work? And that's kind of the way I would think about it, is that can you ignore hurricanes that might be, 100 miles away, but may come your way at some point? And why do we care? And I guess that goes to the heart of basically, is physics complete? Because we do know also quantum mechanics describes the subatomic world. The reason you and I can talk together right now is because we have more or less complete understanding of quantum mechanics, at least on subatomic world, which enables us to use electronics technology and all that. And that's also an extremely successful theory. And these two have to meet at some point. They are different frameworks with very different languages, and all the attempts to kind of combine these two lead to contradictory results or proposals, but they are very diverging proposals. As Phil said, that leads to breakups and also leads to lots of arguments. Some are more constructive than others, but that's that's where things are. So if you want to understand the universe, you have to unify these. Now you could ignore it and may not affect you for your duration of your life, but that also means that you're ignoring part of reality of our universe. And the reason we care about reality is that if we understand our universe better, then eventually we have a better understanding of ourselves and our lives. It may not matter for my life, maybe, but maybe my children or my grandchildren, or maybe philosophically how I approach life or religiously how I approach life. So ultimately, a better understanding of the universe, I think, is better for us, even though it may not immediately impact my life today or tomorrow.
Phil, your view?
Well, so there have been a few cosmologists that have suggested we could try and avoid the whole quantum gravity regime, if you like. It's not a popular view, but Roger Penrose has pushed this perspective. When I spoke to him, he was like, I always thought that when I prove a singularity theorem, it would mean what we've really proved is general relativity is breaking down, and we're going to need a quantum theory of gravity. But then he said he changed his mind, and the idea is that maybe you could get rid of the singularity in some other way. So maybe the universe won't go through into the quantum gravity regime. So his proposal is that actually when you go back to the Big Bang, the temperatures are so hot that you can't actually build a ruler or a clock. So then the universe goes into what's called something called conformal geometry, which basically you can think of as saying big and small are just equivalent to each other. Because in order to say something's big or small, you need a ruler. But if you can't build a ruler, then there's no distinction between them. And the interesting thing is what he said is that my singularity theorem is vulnerable to having this conformal perspective. So if we switch this conformal perspective, then actually the singularity disappears. But there's an interesting consequence of this. It only disappears in the Big Bang. It turns out the Big Bang and the black hole singularities are not quite the same. They're very similar, but they are not identical. And it turns out that even Penrose concedes that this couldn't resolve the black hole singularity. So ultimately then there's still a quantum theory of gravity out there in the universe in this perspective. But whether we need it at the Big Bang, I think the consensus is yes. I think overwhelmingly that's what physicists think. But it's good to point out there are a few minority thinkers that think that we don't. or at least don't need it at the Big Bang. But that doesn't mean that we don't need it somewhere. And I think ultimately then we really want this quantum theory of gravity, and then let's see what it says about the Big Bang and about what happens in black holes. And then we'll find out, is it relevant at the Big Bang, or maybe Penrose's perspective is correct. But if you want to bet with the majority, you're going to bet that we need a quantum theory of gravity.
Now, one glaring thing here in regards to gravity is that it affects time. Mm-hmm. It is in a high gravitational environment, time ticks at a different rate. We know that from general relativity, and it's proven. We know what happens. We know it appears to act like an acceleration does as far as references of time. Mm. Now, that is also within general relativity, the idea of closed time-like curves, which is effectively time travel. Mm-hmm. And let's go there. Niayesh, your view on that. Do you think that you can actually have, in reality, a closed time-like curve that would allow backwards time travel, at least conditionally?
Well, I guess there is the conservative point of view, and then there is the radical point of view. The conservative point of view, that's the one that was advocated by Stephen Hawking, the famous Stephen Hawking, amongst others, was that no, there is something within, even though general relativity allows these solutions that you could basically go back in time and time can go on a loop. If you add quantum theory, somehow there is something that blowing up in this theory, in these solutions of general relativity. So these are sick, basically, space-times. And you cannot really develop those in real situations. But on the opposite point of view, my old professor at Princeton, Professor Richard Gott, he kind of had these counterexamples to Hawking's conjecture, this chronology protection conjecture, which basically was saying that no, quantum theory prevents these time machines. And he had this counterexample. It seemed that you have space-times that had these time machines in them, and they were perfectly fine. Nothing was blowing up in the quantum theory. So there is some kind of theoretical debate, which is somewhat abstract, but the issue of actually building these time machines, it seems a little bit. But that's the part that's hard. I mean, even if you think it's in principle is possible, in practice, how you build it, until you can in practice do this, then it's as if you cannot do it. Now, the part that's kind of gets tricky, and this really goes back to the question of quantum gravity, is that is this problem really a problem if you think in the terms of the full theory of quantum and gravity? And this goes back to this question of basically cause and effect, that do we think causality is a fundamental notion or not? Because, I mean, at the heart of this time travel and going back in time is that, okay, so past can impact the future, but future cannot impact the past. But is that real? I mean, is that an illusion? The same way that, say, wetness of water is an illusion for us. For us, we think water is wet, but really, if you use a very good enough electron microscope, it's made out of molecules, and it's not really a fundamental property. Is causality that everything is preceded by a cause, every effect is preceded by a cause? Is that a fundamental property of physics or quantum gravity, if you want? Or is this an emergent property, something that we only associate to big things that we experience, but fundamentally at the level of an atom, when electrons come in and out of existence in a quantum world, is there a causal description there? And that's where things get murky, especially when it comes to gravity, because our description of what's cause and what's effect is based on a classical geometry where basically things propagate at the speed of light. And then, so you cannot send signals faster than light. But then if this geometry itself is quantum, you're not sure that if two things that are happening, this could be the future of this or this could be the future of that, because geometry itself is fuzzy, right? So you don't know what faster than the speed of light means, because speed of light requires knowing the geometry, knowing how fast you're moving. And if the geometry of a space is unknown, then that's unknown. So I think this becomes a much fuzzier question in a quantum theory, whether you could have closed time-like curves or time loops or time machines. And in fact, one of the proposals, the one that is kind of my favorite, if you want, is something I call it periodic time cosmology, if the entire universe is a time machine. So in fact, our future is the same as our past. So when we go to the future, if you wait long enough, then everything just keeps repeating itself. And it sounds crazy, but we are actually following the footsteps of Roger Penrose. So we're kind of building upon his construction, but we kind of make sure that can you build a universe where everything just repeats itself in this exact same details. And I mean, it's possible. We have predictions for this, but I think ultimately you need a quantum description of gravity to describe it consistently.
Phil, what do you think? Can you go back and prevent the chocolate cake from being baked, or can you make it inflationary by going backwards and changing parameters?
So I'd bet a lot of money that no person is going to build a time machine that lets you go back in time. But that is a separate question to whether the universe ever did that. So I think the technology is just so fantastical that I can't see even the most advanced civilization doing it. But again, maybe the universe could do it. So Niayesh described one idea, which is that the whole universe is on a giant time loop. So if we went forward in time far enough, we'd eventually sort of chase our tail and come back together. That actually echoes an idea from was it Nietzsche, I think, that came up with this idea of eternal recurrence, that everything eventually repeats itself. So a lot of these ideas that physicists play with, and this is something we explore in the book, actually have echoes from philosophers of long ago. But there is another version of this, and Niayesh mentioned Richard Gott. And so there's this famous model called the Gott and Lee model. And this is a really mind-bending idea. The idea is this. So we talked about the multiverse and branching universe structure. And Gott was actually one of the very first people to suggest that inflation leads to a multiverse. In fact, I think he was the first. He doesn't get credit for it much. Usually people attribute it to Andre Linde or Alex Valenkin, but I think Gott got there first. And he was like, well, let's follow this branching structure backwards in time. And he speculated that maybe eventually there, at the origin of this sort of branching universe structure, you will find a little time loop. And then the universe has sort of two realms, if you like. A realm in our distant past where time travel is possible, and then we escape out of the realm and we're in that part of the universe where time travel is not possible. So we cannot go back in time and stop our parents from meeting or kill our grandparents or whatever movie is your favorite time travel movie. Mine's definitely Back to the Future, although Predestination is a good one too. But anyway, so if there's this origin time loop, then the universe could, if you like, become its own mother. But that would not allow us to time travel back into the past. So this is a super, super exciting model. I remember reading it for the first time and thinking, of course, that explains the origins of everything, because you always want to know, well, what happened before that? And if I tell you there was a bounce, suppose I said that would be fascinating to learn. How profound would that be, to find there was a collapsing universe before ours? But you still kind of want to know, yeah, okay, and what happened before that? And what happened before that? And what happened before that? And the idea that, well, it's all just a circle, what happened before that is what happened after that. Something seems almost satisfying to me about that. Like, I find it very, very attractive idea, but it's hard to test. Niayesh's model, I think, is more predictive than the Gott and Lee model. And I asked Richard Gott how he could test it, and he was like, well, maybe we'll come up with a quantum theory of gravity and then it will tell us whether this is what happened. But there's no firm predictions from this model, unfortunately, whereas Niayesh, and he worked with his student Elizabeth Gould on this, I think is more predictive. So maybe we could find out if that model was right. And there's another profound, I've just had this idea, and Niayesh checked me on this, that this model, the periodic time cosmology, requires the universe to be spatially infinite. So if we could confirm this model is right, not only would we know that the universe is on a time loop, but we'd also know the universe is infinitely big. What a profound discovery that would be.
That's right. That would be fantastic. Yeah, no, it's certainly our model requires the universe to be infinitely big. Otherwise, it wouldn't work.
But the idea of an infinitely expansion, an infinite universe, the idea of that comes with a whole lot of baggage, because then everything starts repeating again, right? In other words, you find something very similar to Earth if you go far enough, as I recall. Is that the way that works, Niayesh?
Yeah, well, it's kind of the way probability works, that if you have an infinite universe, and if it's random, then you would find arbitrarily close copies of everything. Now, I should confess that this is a bit different in our model, because this process of matching the future and the past, it requires various scales to be kind of matching to each other. So I'm not 100% sure that this is true, but I think some version of this would be probably true, that there would be copies similar to us far away. In fact, there are our model is interesting in the sense that they're not, in fact, there are infinitely many copies of us, but at various stages of evolution. So like if they say, imagine we live here on Earth, at the same time, there is a copy of us, but from kind of a state that Earth hasn't formed yet, or Milky Way hasn't formed yet. It's just much bigger scale, which is kind of some diffuse gas. It exists now at the same time as we do. So in fact, there are infinitely many of us in our universe, but in various stages of our life, basically. And by life, I mean like the cosmic life, not just life of me, like not 100 years or so. So yeah, so in that sense, that exists there, but we're not at the same stages of life, at different stage. And then if as the universe goes through different cycles, then like it's this kind of a reincarnation, if you want, that we kind of match. I go to a more evolved stage of myself, and a kind of a less, more primitive stage of me would map to the current stage of me, basically. So that's the way that our model works. But of course, this is one of many possibilities, and I like it. I find it tantalizing, but that doesn't make it true. It's just imagination. And I think, as Phil likes to mention it, Feynman famously says that science is imagination in a straitjacket. So I like the imagination part. The straitjacket part is not as nice, but we have to deal with it.
In a way, though, that almost looks like time travel, because if you have a near copy of Earth, the system out there, but it's in a younger state and it's still dinosaur planet, then in that sense, it becomes classically possible to go back in time just by virtue of infinity, right? Phil, answer that question. Am I crazy?
You'd have to travel quite far, I think. That would be your problem. But maybe if you could put yourself in stasis, maybe. I mean, I think, the famous physics blogger Sabine Hossenfelder has suggested that she thinks fast and light travel might be possible. I'm not sure, but if it was possible, maybe you could do this. But there would be those impediments in your way. Could you live long enough? Could you travel fast enough and far enough? But I find it a very exciting, appealing idea. Some people hate the idea that there could be sort of other copies of them out there somewhere. But this idea keeps popping up. I mean, in the multiverse idea, you have this. This is a different idea to the multiverse, but yet the idea of copies of you pops up again. I like it because I kind of think, well, I'm only going to live so many decades and then I'm going to die. But I like the idea that somewhere out there's another me, where they'll wake up, the day they're born and live out the whole thing all over again. It's maybe some kind of scientific version of an afterlife. It's not, you wouldn't have the continuity of consciousness, but it is some version of an afterlife, maybe.
It's a fascinating idea. Niayesh, what do you think about that? The broader implications of there being copies of us out there?
Well, I don't know what to make of it. It's one of those things that you follow the rules of science and takes you what it takes you, and then you then sit down and stare at it and say, okay, is this where I wanted to go? What do I do about this? And I'm not saying that that's by any way a prediction of science, right? As things stand, it's still a speculation. But I think it gives us a new perspective on life if it turns out to be true. And but again, it's one of those things that you wonder, what's the purpose of life? I mean, what is our goal in life? And I think the first step is to understand what we're doing and what's happening. And then with the best of our understanding, we can decide, okay, we can decide what our life is worth. But I mean, I don't really have any answer to that. I think I marvel at the possibility, but my immediate reaction is that how can we test it? And that's where I'm right now.
Yeah, testability is always the problem in astronomy, because as you mentioned earlier, it's just so limited on what you can test, and it becomes a lot of guesswork at some point. Now, let me ask you this. Now, we mentioned early on the quantum fluctuations during inflation, and these temperature fluctuations anyway are preserved in the cosmic microwave background radiation. We see that, the anisotropy of the universe. What would have happened had that not been the case? In other words, what if the temperature had been uniform? What would the universe look like, Niayesh?
That's an interesting question, and in fact, this was a puzzle for like 20 or 30 years. So the cosmic microwave background was first observed in 60s. In fact, Just one thing we highlight, in fact, if you go back into 1940, a Canadian discovered cosmic microwave background, but it was an indirect, if you want, observation. It wasn't a direct observation. It was based on temperature of interstellar molecules. But then the direct observation of cosmic microwave background was by Penrose and Wilson in 1960s. But for basically almost 30 years, there was this puzzle of why is this so uniform? Like every direction we look, the cosmic microwave background was the same temperature. But then the wonder, okay, so how do we form structures, galaxies, planets, stars, if the beginning was so uniform? And yeah, so that was a big puzzle for almost 30 years. Fortunately, in 90s, basically in 1990, Kobe satellite for the first time discovered anisotropies. And in fact, one of the reasons that it took so long was, in fact, we thought anisotropies fluctuations should be 1 in 1,000, but in fact that prediction ignored the fact that there was a dark matter in the universe, so we didn't know about dark matter. So it turned out that just 1 in 100,000 fluctuations was enough to give our galaxies the way they are, because there is a dark matter, and that kind of changed the predictions. But yeah, I mean, then it would have been a big puzzle if the microwave background was completely uniform. Then presumably nothing would have formed. Universe would have stayed uniform. Of course, there are quantum fluctuations, but quantum fluctuations is far smaller than what we see, kind of the structures we see today. So that wouldn't have done really much. The universe would have stayed uniform. So you really need something to generate fluctuations or non-uniformities in the initial conditions of universe. And all the theories, or all the successful theories of our universe, have some mechanism to do this, either through quantum fluctuations or thermal fluctuations, or basically just randomness in early initial conditions, to give you these things that we see in the microwave background. Because in fact, the most successful, the most precise measurement in cosmology is measurement of the fluctuations, or the pattern of fluctuations in the cosmic microwave background. So that's kind of a litmus test for all the theories of cosmology, and many theories of the cosmology are now dead because they couldn't really fit these patterns of fluctuations.
Now, Phil, this is an example of a very small effect, almost immeasurable present, defining how the universe is as we see it today, telescoping to become something very big. What's your view on that?
Well, it's incredibly profound, isn't it? I mean, to think that our huge universe stretching across tens of light years, billions of light years, that originated from something quantum, subatomic, is absolutely mind-blowing. Now, whether it was the cold quantum fluctuations as an inflation, or as Niayesh mentioned, these thermal fluctuations, they're different. This is kind of one of the big battles that we talk about in the book. How do you generate these fluctuations? And we're taught that it's inflation, stretching, quantum fluctuations. But what we're not often taught is that there are other mechanisms. So it could be something like, imagine, a fire. If you look at a fire, some parts will look hotter than others. They're a bit more yellow than others, a bit more darker than others. So the origin of these fluctuations doesn't have to be via the inflationary mechanism. There are alternative theories to inflation that give a different way to generate these fluctuations. But nevertheless, this is how we're going to test these theories. Do they generate the right spectrum of fluctuations? And then, of course, there are other things that we haven't yet observed, and we haven't talked about gravitational waves yet. But this is one of the key ways that we might differentiate between the battling theories that we describe in the book. Some of them predict there should be noticeable gravitational waves. Some say there won't. Some say that they'll have a certain spectrum. Others say a different spectrum. So this is what I'm most excited about. The cosmic microwave background is an incredibly useful tool for probing cosmology. But I think we can go further and look at the gravitational wave background. Is it there at all? If so, what properties does it have? And that's what excites me. That's for the future.
A gravitational wave background, however, breaks the rule that you can't see too early into the Big Bang. You can't see, 300 million years, something like that, after the Big Bang.
380,000 years after, yeah.
Yeah, 380,000 years, that's correct. And you can't see before that, but that gravity is not beholden to that, right?
Yeah, that's right.
Yes, that's an amazing thing. And so, in fact, there's an example of that closer to home. So the sun, we cannot see inside the sun. The sun is dense and opaque, so we can see the surface of the sun. And in fact, the story of cosmology is very much similar to the sun. We cannot see inside the sun, but there are indirect ways we can probe it. Now, the sun, it turns out that vibrates and fluctuates. It's like have sun quakes, if you want. And measuring these quakes in the sun is very much similar to these fluctuations we see in the cosmic microwave background. So there's like sound waves that were generated at the Big Bang. We don't directly see the Big Bang, but the sound waves have propagated. And by measuring what's happening at the surface, the so-called surface of last scattering, is similar to seeing what's happening at the surface of the sun. And from that, we could infer what's inside the sun. But then there is another probe. There are neutrinos, that these are these weakly coupled particles that travel the universe, and they are generated at the core of the sun where there are nuclear reactions. Those neutrinos can travel freely through the sun, almost freely, because there are some interactions, but they're very weakly interacting. And we have now detected these neutrinos. In fact, we've detected them for several decades now from the sun. And then that has helped us understand the model of the sun and also the model of neutrinos to some extent. In fact, Canadian Art MacDonald here won the Nobel Prize for it in the Sudbury Neutrino Observatory in Ontario. So gravitational waves are there are actually neutrinos coming from the Big Bang, but they're very, very hard to see. I mean, people are trying, but that's kind of one of those hard battles that I think the harder battles to fight. But gravitational waves is another thing because they are even more weakly coupled than neutrinos. So basically, because gravity is just weak, the weakest force of nature, and they can just travel freely through the cosmos. And if they are generated at the Big Bang or near the singularity or instead of singularity or even from before the singularity, before the bounce, if there was a bounce. So if we could detect them, they give us unimpeded view of Big Bang or whatever happened before the Big Bang. And that would be fantastic if we could detect them. But these are all hard. The issue is we don't know how much gravitational waves comes out of the Big Bang. About 10 years ago, there was this claim that they were detected. There were lots of big press releases, the so-called BICEP experiment that detected Big Bang gravitational waves. Turns out that wasn't real. Turns out that it was dust in our galaxy. Unfortunately, the celebration was a bit premature, but everybody thought inflation is confirmed, and there were talks of Nobel Prizes. Turned out they all turned into dust, literally and figuratively. But we still may detect them in the future with better instruments. Or if we don't detect them, that's going to rule out many models of inflation and possibly other models. And gives us one more tool in our arsenal.
Yeah, that's important. A non-detection is just as good as a detection in astronomy all too often. Now, Phil, what do you think about the future of trying to detect and study and characterize the neutrino background and also the gravitational wave background? What do you think in our lifetimes we're going to make that and have an understanding of it?
So actually, it's funny because we had a bit on the cosmic neutrino background in the book, and it got cut. So I'm trying to remember what we actually said about the cosmic neutrino background. It's very, very difficult. I've spoken to neutrino physicists, and it is very, very difficult to detect. But they have ideas, and it's not impossible. And that, I think, neutrinos would give you information. So the cosmic microwave background is 380,000 years after the Big Bang. Neutrinos would be something like 1 second after the Big Bang. So it would be absolutely fantastic if they could be measured, but it's very, very difficult. The gravitational wave background, of course, is even earlier than the neutrinos. So I think the focus of the cosmological community is the hope to discover gravitational waves from the Big Bang. And there's a couple of ways it could be done, where Niayesh mentioned the story of BICEP. And what they actually did, they didn't try and see them directly. The idea is that they create certain patterns in the cosmic microwave background. They're called beam modes. So you could look for those, and that would be a sort of indication of information of these gravitational wave backgrounds. They imprint on the CMB. So that would be amazing to see. And hey, we could discover that tomorrow. It's not impossible. People are looking for them. Yes, we had this false alarm and the story of the false alarm. I think it's fascinating in itself. I really, when we were writing the book, that was one of the most fun parts to write about, because it's such a, I think, intriguing story of the history of cosmology and the hubris and and the rush to publish. And so it's a fascinating tale. But we can push beyond. And there's another project, for example, to look for them in space. There's a few projects. Lightbird is a satellite being proposed by the Japanese Space Agency. They're looking at the polarization of the microwave background. And that has been approved at some stage, but the full funding is yet to come. So I think what will happen, my guess is what will happen is if we get a detection from the ground, then it's been recommended that space-based detectors will be then a priority. Whether a government will commit to them before we see anything from the ground. Obviously, thinking about space-based detectors, they're better. They can see the whole sky. I mean, they have many advantages over a ground-based detector, but obviously they're more expensive. So I think the thinking is, yeah, maybe we'll get lucky and see a signature from the ground. That will give the impetus then to put space-based detectors up. Some governments might take a gamble and say, let's put the space detectors up anyway, because the discovery will be so profound, so incredible, so exciting if we were to discover this, that it's worth it. You know, we could launch another satellite. So Lightbird is one from Japan. There's India have one. I forgot the name of it. Niayesh, remind me of the name of it. Do you know?
Yeah, it's off the top on top of my tongue. I can't remember exactly. Yeah.
There's another one from the Americans. I think it's called Pico. Is that the latest proposal? So there's all these proposals. They're on the drawing board, and I think they could certainly happen with our lifetime. Beyond that, there's direct detection of gravitational waves, you know, from something like LIGO. Some people will be familiar. I hope. I imagine your listeners will be familiar with LIGO. Detected gravitational waves from black holes using laser interferometers, and that was absolutely a tremendous discovery. I think it got one of the fastest Nobel Prizes ever. Didn't they get the Nobel Prize like 1 year after it was discovered? Usually
2 years, I think.
Is it 2 years? Yeah. Usually you wait decades and decades.
Yeah.
But it was so profound. So could we do that on a bigger scale? You know, well, European Space Agency are launching something in the 2030s. This is fully funded and in development. It will be launched in the 2030s. The Laser Interferometer Space Antenna, LISA. So that's going to go way bigger than LIGO. We're talking arms that are not 4 kilometers long, but I think 2 million kilometers long, if I remember rightly. So that can go to different frequencies. Now, that won't necessarily try and detect gravitational waves from the Big Bang, but what it could do is to test maybe quantum gravity theories for supermassive black holes. Maybe there's a chance to see some effects there. And Niayesh can talk about some of his favorite black hole echoes. And then beyond that, you know, there are even bigger and bolder plans to do the successors to LISA, and they would look for gravitational waves directly from the Big Bang. And that's probably the most ambitious thing that we can sort of dream up. And that for sure is decades away. But, you know, it's something people are already dreaming about, because we have this insatiable quest to understand our origins. And when we do, if we want to do that scientifically, we have to put these theories to the test. So in the Battle of the Big Bang book, we talk about all these exciting theories, and they are super fun to speculate about. But ultimately, they've got to be tested with data. And I think something like a giant laser interferometer in space will probably be our best bet to do that.
Now, I have a couple individual questions, and we'll start with Niayesh. Now, in the book, Niayesh, you describe growing up near Tehran in Iran and being an amateur astronomer back then. What was that like, growing up in Iran and doing amateur astronomy? And how does how we view astronomy differ between East and West?
Yeah, it's an amazing contrast. That it's good you're asking me these questions, and hopefully this will be recorded then on YouTube and our podcast, because I left Iran 26 years ago now, and so the memories are getting fuzzier. I'm kind of starting to forget things. Of course, I mean, when you're younger, everything is different. I was growing up I was born during a revolution, the Islamic Revolution, which started the Islamic Republic of Iran, and there was a very long war happened shortly after I was born. So it was a very different place to grow up compared to here in the West. But that was the way that was life as I knew it. The astronomy part was kind of amazing, because I fell in love with the sky because of how kind of peaceful it was. I think actually I wanted to be an astronaut at first. So I was just collecting all the things all the record of like Russian, American astronauts going all over the place. And at some point, I think I gave up on that because I thought, okay, so that's not going to happen. So I kind of became content with just astronomy and observing the night sky. And that was amazing because you didn't need anything to do that, and it was so quiet and peaceful. And then I found a club of people who were interested in the same thing, understanding and observing the sky. I fell in love with astronomy books. And it does also, I think, gave me a different perspective in astronomy, maybe compared to many others, because in some sense, this battle of religion and science, which we're kind of familiar with in the West nowadays, and it's been ongoing. There it was very strange. And of course, there are also the sort of negative aspects of religion that was affecting daily life. But on the other hand, astronomy was part of religion because all the kind of religious celebrations and events were dictated by astronomical events like lunar sighting the moon, right, the first crescent after the new moon, or when the prayer times. They're all based on astronomy. So in some sense, all the religious people had to know some astronomy or learn from or rely on someone who does use astronomy. In fact, my uncle, who runs a mosque in Toronto, he always contacts me when the Ramadan starts and when Ramadan ends. And so because it relies on sighting of the moon. So it's an interesting kind of complex relationship between astronomy and religion that kind of stayed with me, even though I'm a different person now, living in a different world.
It's interesting, too, because it goes back so far, because you can look at pre-Islamic coinage from Iran, the Parthians and Sassanid dynasties, and see depictions of the crescent moon, on the coinage, and showing that it meant something to them as well. And I think they were big into astrology as well, predictions and things like that. But it's just that there's this enormous thousands and thousands of year history of Persian astronomy that's still going on in Iran today. Phil, what brought you on your path to try to figure out what exactly happened regarding the Big Bang?
So my path is quite different. I also have had a love affair with the sky ever since I can remember. One of my hobbies is skydiving. I just love being up in the sky and observing it too. So I have a passion for astronomy as well, and I'm an astro imager. I have a pretty good telescope, and even in the city we can cut right through the light pollution. I actually, one of my images was featured on the BBC Sky at Night program, and they said this image looks like it was taken by the Hubble Space Telescope, but actually it was taken by a guy in his back garden in London. So I think when you look up at these objects, you start wondering, well, where do they all come from? So my path was, I got into amateur astronomy and I wanted to just learn more and more about the subject. So I went back to university, did evening classes in astronomy. But I got really fascinated with early universe cosmology because I've always been interested in origins questions. I mean, I think they're fascinating. But my teachers, they weren't specialists in early universe cosmology. So I realized that, I wasn't going to get all the answers I wanted from the course. Not that the course wasn't absolutely wonderful. It really, really was. And I highly recommend UCL as a place to study. So what I decided to do is I wanted to watch material on YouTube that would explain some of the cosmological models that I was aware of, and there just wasn't anything. And someone suggested to me, well, you know what, if you want to watch this stuff, why don't you make it? And I thought, okay, I will. So I started writing to cosmologists and saying, I want to make a film about your model. And the first one I did was actually on loop quantum cosmology, because I'd read so many books on string theory, and they might have like one line saying, oh, there is another theory called loop quantum gravity. And I'm like, well, okay, look, your string theory hasn't been verified yet. We don't know if it's right. Let's hear about this other theory. And there was nothing around at the time. This was before Carlo Rovelli got his gig as a popular science writer. So I made a film with them, and that was the first thing I made. It wasn't very well made, I'll be honest. I didn't know what I was doing. And in fact, we remade it when I did know what I was doing and I could film professionally and so on. But the first version got hundreds of thousands of views. I thought, yeah, people are interested in this. I'm interested in this. So I carried on and made more. And eventually I just ended up talking to all of the leading cosmologists, even Stephen Hawking. I spent some time with him, went to Rome with him. So that was my path. It was kind of an accident. It's just someone wanting to understand something, and the only path to do it was to speak to the experts directly, and that's what happened.
That's what I do. I do it every week. Everybody should check out their new book, The Battle of the Big Bang, The New Tales of Our Cosmic Origins. And gentlemen, thank you for joining us today. And will there be another book after this?
Oh, I don't know. This was a very, very long project. So I think we'll take a breather and we'll see what happens. But yeah, it's been an absolute pleasure. Thank you so much for having us on.
Thank you very much, John. It was fun. I think someone asked me this question, and I had this experience of having a kid. Well, not myself, but with my wife, and then I think at the beginning they say, okay, never again, and then after 4 years, maybe then they kind of be warmed up to the idea, and then we had a second kid. So I think we have to wait a few years and then see whether we can get back to it or not.
Thank you, gentlemen, and I hope you'll join us again sometime, no matter what happens.
It's been a pleasure. Thank you.
Thanks.